Okay, so as I mentioned, our plan is to review the chain rule. We're going to look at homework questions, and then we're going to take a look at implicit differentiation. Just a word, maybe some of you have discovered this. I put out solutions to the evens on Edmodo. So in particular, number 56, number 18, take a look on Edmodo for solutions to that so you can check yourself out. Our story with chain rules so far has been a story of ADX of f of g of x. And at this point, all of you have probably learned the form. It is. It's what? Very good. Form is the crucial part, and the slogan helps us to remember it. Derivative of the outside times derivative of the inside. Excellent. And so if we write this in Leibniz notation, we would say that if y is equal to, for example, f of x, then dy dx can be expanded in terms of any variable u as dy du times du dx. And although it is not exactly conversion factors, it has that appearance. We're looking at two different rates of change. The rate of change du dx converts dy du into dy dx. Yes? It looks like cancellation. It's not really, because this is not really a quotient. This is not a little piece dy divided by a little piece du. It's really the limit of a difference quotient. So it's one limit times another limit. However, Leibniz actually is going to think about this in terms of quotients of little pieces right there, and that's why he writes it like this. And his concept is close enough or robust enough to make it all work. Okay. Good. Now, questions about homework? Does anybody have any? I do have a book. Somewhere. Here. Uh-huh. One of the problems I know that showed up for in the other class was number 27.
Square root theta times
And I also wanted to take a look at number 9 from the previous assignment on page 146. And here we had y equals cotangent x over 1 plus cotangent x. And they wanted y prime. So let's take a look at those two. In the case of number 27, so they asked us to find the derivative. Notice the spelling of the derivative. It's not dy dx, it is dr d theta. So here, r is playing the role of our function, and theta is playing the role of the independent variable. And so we're going to take the derivative with respect to theta of theta sine theta, like so. You could also spell this as r prime of theta, but I chose this spelling right here because the book asked for that. Either one of these is perfectly fine. They're synonyms. Lagrange notation, Leibniz notation. So, how do I proceed?
outside is 0 and inside is 3.
Good. Very good. And so our derivative is?
1 over square root 3 that's not 3 times square root 3 that's not.
Good. Okay. Now we examine this theta sine theta thing, and what derivative rule am I going to need for that? Yep. And So at this point, I think you are experienced enough with the product rule that you can go ahead and do that in one step here. So this would be, uh-huh. Times 1, that's right. D theta is equal to 1. Now, there was some question about that in the other class about the variable here. But what I'm doing is taking the rate of change of theta with respect to theta, and that must always be 1 because as theta changes by a certain amount, theta will change by that same amount. So the rate of change is always 1. Okay. Whereas if I were, so d theta, dd theta of theta is 1, whereas if I were to take the derivative of theta with respect to x, I would get something really different. I would get d theta dx. So notice that the variable matters here. I cannot just interchange x and theta as if they were the same thing. What they have in common is that they are commonly used as an independent variable here, but they are not the same variable. So I can't just swap them out. Okay? And so finally, when the dust settles, I get theta cosine theta, sine theta, all over 2 roots theta sine. Yes, sir.
Nice plan. Oh, thank you.
You can stop at any point where the calculus is done, if you need to. One of the things, however, that you should be doing is checking your answers. And so when you check in the back of the book, you're going to see it written like this. And so you want to be able to take your answers and put them into this form. Speaking of, let's take a look now at number 9 from page 146. This guy right here. And I think we're going to need more room, so let me group this and we'll send it to another page. There. They wanted y prime, and so y prime is going to be equal to ddx of. And I believe when you guys did your work, all of you did this with quotient rule, and I think everybody did it correctly, but we'll go ahead and walk through that process. Low be high, less high be low, and give myself a little room to work. One of the ways in which I think I need to get better as a teacher is in predicting how much space is going to, things are going to take, so that I'm going to move things around. So this is all good here. I had some students in the other class who forgot their parentheses. You do not want to neglect your parentheses because this expression right here, 1 plus cotan x times the derivative of cotan, has a different meaning than this expression right here. This would mean cotan x times the derivative of cotan x plus 1 because of order of operations. The multiplication happens first. With the parentheses, it means something completely different. Cotan x plus 1 times the derivative of. So just be careful about your parentheses, that you are expressing, you're saying what you want to say. Now we come through, and we take the derivative here. What is the derivative of cotan x?
Negative cosecant.
There you go. And so this is all more or less happy. We need to simplify here, and so we get negative cosecant squared x minus cotangent x cosecant squared x plus cotangent x cosecant squared x all over 1 plus cotangent x squared. And we observe that we have like terms that cancel out. So we get our answer. And I think all of you that did this problem got this answer, and it's perfectly fine. Then you look in the back of the book. And the back of the book says -1 over sine x plus cosine x squared. And you go, huh? Now, some of you handle this in different ways. I had one person who said, the back of the book says this, and I got this, and I have no idea what's going on, basically. And that's perfectly fine. A couple of you just said, got this, equals that. No justification. Just, that's my answer. You don't want to do that. And the reason that you don't want to do that is that seeing the back of the book answer be in a different form from yourself is actually an opportunity now for you to learn some algebra. So let's think through. If we assume that this answer and this answer are both possibly correct answers, then it must be the case that I can transform this into this using valid algebra. What do I need to do to this guy if I want it to look like that guy?
1 over cosine. No, it's not. Well, times 1 over 1 plus cosine.
Probably I want to rewrite that one too.
Oh. Then,
No. Sine and cosine. So this is a basic strategy that we have if we have an expression in terms of cosecants and cotangents and so on and so forth. And that is expressed in terms of sines and cosines. So I can take everything here and replace it in terms of sines and cosines. And what inspires that is that the answer I'm shooting for is in terms of sines and cosines. Right? So this is strategy number 1. Replace everything in terms of sines and cosines. Now, next thing that I have is I look and I see that I have a complex or compound fraction. Complex fraction. So what strategy have we used to deal with that? What's that? Where from here?
so multiple denominator top sine squared x.
Good. Multiplying top and bottom by sine squared so that we can clear the compound fraction. See it? So clear the fractions is a slogan that I want you all to adopt because these compound fractions show up a whole lot and we need to be able to handle them. Okay, so now I simplify here. Clara, how does my numerator simplify? Okay, and my denominator? Well, my denominator is what it is. So let me write my denominator, and then we'll take a look at what we have. And I'm encouraged when I look because I see that the -1 here in the answer matches the -1 there in the answer, and that tells me that maybe I'm on the right track. Then I look at this guy right here, and I look at this guy right here, and I realize that if this is going to work, they somehow had to merge these square things together. And so I do a quick computation over here. A squared b squared is the same as ab squared. So, therefore, if this is my a and this is my b, this is -1 over 1 plus cosine x over sine x times sine x, and all of that squared. But now when I distribute, look at that. Look at that. And so it all works out. Now, you guys remember that my basic philosophy is don't simplify unless you need to. Unfortunately, one of the places where you need to simplify is so that you can check your work. And if they give us an answer like this, and my answer is like this, then I am not going to do one of two things. I am not going to look at my answer and look at their answer and say, oh, I'm wrong. Because there is a good possibility that my answer can be converted into their answer. And the second thing that I'm not going to do is to look at my answer and look at their answer and say, oh, I'm right, these are equal, without actually checking them. Because both of those processes, assuming you're wrong and assuming you're right, short circuit the learning that happens here with regard to the algebra. Everybody's algebra needs to get better, faster, stronger, and the way it happens is by these kinds of things where you know the answer ahead of time, but you have to get there. Does that make sense? So do not avoid that process of reconciling your answer with the book answer. Do the reconciliation so that you can check. Okay? It's a matter of being a smart student. Okay. Any other homework questions? 56. I put out an answer to 56 on Edmodo, and so I'm going to let you take a look at that. Answers to evens, it says.
It's under the replies for the assignment sheet.
Somebody said, can you put up answers to the evens? And I replied.
Mark
Yeah,
Mark.
it's under the replies of the weekend.
I see. Yep. Okay. All right. Let's talk implicit differentiation. Before I get started here, I want to do a chain rule review in this way and ask a really interesting question. What do I get when I compute d dx of f of y? That's not a mistake. I have two variables in there on purpose. What do I get when I compute d dx of f of y? Times 0. Yikes. So it's always 0? Times 1.
Depends on like the primal
Oh, times y prime. Yes. That's what you really meant. Yes. This is straight up chain rule, isn't it? Derivative of the outside times the derivative of the inside. We could write this as f prime of y times dy dx. So the chain rule simply gives us a way that I can differentiate a function of y with respect to x. And that is, first I differentiate it with respect to y. And then I convert it by multiplying by dy dx. Hello? Thank you. Okay. Now, keep this in mind here because I want to consider a relation between x and y that is not a function. And that relation here is x squared plus y squared is equal to, I'm going to make this 25. I did 4 in the other class, and 25 helps simplify my life a little bit. Now consider this relation right here. First of all, what shape of curve is formed by this relation? It is a circle. What is the center of that circle? What's the center of that circle? Is the origin. And what is the radius of that circle? 5. It is 5. Exactly so. And the reason that this is a circle is that if I pick any point x comma y right here, and I take a distance of 5 away from the origin, so that this side has a length of x and that has the side has a length of y. If I apply the Pythagorean theorem directly, look at what I get. Ta-da! So that this equation is expressing the set of all points in the plane whose distance from the origin is 5. In other words, a circle. That's it. Now, here's the thing. Given that the graph of our relation is a circle, is this relation a function? No. Why not?
Well, the vertical line test, but
Right.
here's, yeah.
It fails the vertical line test, so we put it here, not a function. So geometrically, we say it fails the vertical line test because I can find at least one point, in fact, I can find an infinite number of points, for which 1x gives me 2y. I can see the same thing algebraically if I try to solve for y as a function of x. If I subtract x squared from both sides, then I find that in fact I have two different solutions for y for any given x value. One is the square root of 25 minus x squared, and the other is the negative square root of 25 minus x squared. And each one of these corresponds to a different branch on my circle. Y equals the square root of 25 minus x squared corresponds to the top half of my circle, where I have positive y values or non-negative y values. And the bottom half corresponds to y equals negative square root of 25 minus x. So this is not a function, and yet, can I draw lines tangent to my circle? Yeah, I sure can. I can go to some point right here. Maybe my point is 3, 4. And I can draw a line that is tangent to my circle at the point 3, 4. And it's not too hard to see that I can do that at any point, really. Maybe I have trouble at the edges where my tangents are vertical. But other than that, my function, my relation, appears to have a derivative or a slope of the tangent line at every point x, 1. So I need a way to find it, and I need a way to find it that does not depend upon x alone, because at the same point x, I'm going to have actually two different slopes of tangent lines corresponding to my two branches. So the question now is, how do I differentiate? Yes.
For the graph,
Yes.
0, negative 5,
Yes.
is it like kind of horizontal tendency?
Yes, it is.
Is it like vertical tendency?
Right here at negative 5, 0, and right at 0, 5. Okay.
Or do you learn,
5,
do
0.
you learn vertical?
Yes. A vertical tangent is a place where dy dx is infinite.
Oh, okay.
Yeah, yeah. Good. Okay. So our question then is, given this relation, how to find dy dx? And it turns out the answer is delightfully simple. We're going to find dy dx by taking our original relation right here and finding its rate of change with respect to x. And this process we call implicit differentiation. And it's called implicit because rather than writing y equals f of x, an explicit representation for y, instead we are going to take a relation between x and y. And let me, for the sake of your notes, I'm going to okay. For the sake of your notes, I'm going to write that relation right here. I'm going to take the relation and I'm going to find its rate of change. And here's the logic. It's really simple. if x squared plus y squared, I said 4, and that's my other class. 25, 25, thank you. If x squared plus y squared must always be 25, then the rate of change with respect to x of x squared plus y squared must also equal the rate of change of 25. See? Simple logic. But now, how do the mechanics work out? Well, first of all, I consider the right-hand side because that's easy. ddx of 25 is? 0, because constants don't change. Now, I walk down through here, and I observe what I've got here, first of all, is ddx of x squared. That's easy.
2x.
But now I have ddx of y squared. Yes, we do. Yes, we can. Because ddx of a function of y is f prime of y times dy dx. Yes, it is. And so the way we handle it is we're going to differentiate with respect to y, and then convert with the chain rule times dy dx. So our first step in our process is to take the derivative of both sides with respect to x. ddx both sides. Sounds like a wrestling. ddx. Then, having done that, now the rest is just algebra. We're going to solve for dy dx with the usual algebra. Too many steps in my mind. Here we go. I'm going to collect all the terms that have dy dx on the left over here. I'm going to collect all the terms that do not have dy dx on the right over here, and then divide. Yes, isn't that an interesting expression? Notice that my dy dx here has a value of the slope of the line tangent that depends not only upon the x value, but also on the y value. Oh, wait a second. That makes a whole lot of sense. Because the slope of my tangent line depends not only on the x value, but also on which y value I have. So that when xy is 3, 4, dy dx will be equal to negative x over y, or negative 3/4. And when xy is 3, negative 4, then dy dx will be equal to the opposite of 3 over negative 4, which is positive 3/4. So that these two tangent lines have opposite slopes. Cool. So what we find then is that when I have a relation between x and y, I can differentiate that relation and find dy dx in terms of x and y, so that I now have a unique tangent line slope at each point x comma y on the curve. What do you think? Does this make sense? What questions does it raise in your mind?
So if we have only 2 points, we can.
Yes. Generally, you can.
Without formula.
Well, we have a formula. It's just an implicit formula rather than an explicit formula. At no point here do I discover what y is in terms of x. I just
The formula of the function. We can differentiate even if we didn't.
yes, exactly. Exactly. Okay, so let's take a look at another one. Let's imagine that we have an interesting curve. X squared y plus y squared x is equal to 2. Interesting. Now here is an unfortunate fact about your calculators. Your calculators are not going to be able to graph this because you can't put it in the form y1 equals. So in general, these the relations between x and y will not be graphable on your calculator. However, there is a website that does do graphs for you, and I'd like to show you that website for just a moment. It has a paid for portal, but it also has a free portal. And so the free portal allows you to go and graph Wolfram alpha. And if I pull up the free portal right here, and I ask it to graph the relation, what was my relation again? X squared y plus y squared x equals 2. X squared y plus y squared x equals 2. See how I'm using the caret sign for the exponent right there? And hit enter. Then it will think for a second, and it will go and plot all the points in the plane for which x squared y plus y squared x is equal to 2. And that's a crazy graph. Isn't it wild? And so now I wonder, what is the slope of the line tangent at any point along this curve? Like here, or like here. I also wonder, are there any places where the tangent is horizontal? Like that. We'll come back to that question tomorrow, right? Or is there a place where the tangent is vertical, like that? Okay? So we're going to find an expression for dy dx, and we're going to do it exactly as we did the previous one. Crazy graph. Kind of a fun graph, yeah.
For at least at x equals 0.
At x equals 0, it appears that the graph simply does not exist. And that actually makes sense. Because if x is equal to 0, notice that I get the equation 0 equals 2. And that never happens. Okay, so to find dy dx then, we're going to walk through the process of taking a derivative with respect to x on both sides. And again, the logic is that if x squared y plus y squared x must be 2, then the rate of change of x squared y plus y squared x must equal the rate of change of 2. So we ddx both sides. On the right-hand side, easy.
0.
On the left-hand side, we're going to walk through carefully taking the derivative. Now, here's where a lot of students fall apart. If I pronounce this relationship carefully, it is x squared times y. That's a product. So I need to first use the product rule. X squared times the derivative of y. Notice how I spell the derivative of y with respect to x. Plus y times the derivative of x squared. And then for the next term, we have y squared times the derivative of x plus x times the derivative with respect to x of y squared. That's a little bit cramped, but is everybody clear on what's happening? So I had to be careful about product rule. I'm just going to shout right here. Don't forget product rule. Very common thing that happens. Okay. Now, let's clean up. I have x squared dy dx. I like writing it as y prime very frequently. Plus now y times, what is d dx of x squared? 2x. So that's just 2xy then. And the only reason I write it as xy and not yx is alphabetical. Plus y squared times 1 plus, now what is d dx of y squared?
3 y
Okay, but what is that? d dx of y squared. I think you were right. Say it again louder. Not 2. differentiate with respect to y, what do you get? 2y. That's right. That's the derivative of the form, the outside. Now, convert with the chain rule times dy dx. So think of it as a two-step process. First, derivative with respect to y. Then, times dy dx. Does that make sense? Yep. And all of this is equal to 0. Yes, sir.
45 by dy squared over dx. What's that equal to?
If you are ever finding yourself writing things in this form right here, for example,
No, dy squared. Y squared over dx.
There's a
sort of like that,
there's the whole thing dy squared over dx.
what does that mean?
Derivative of y squared.
With respect to x? Well, yes, but that just pushes off the question. That's the question that I asked right here. This just pushes off the question. This is the question I asked right here, right? And your response is,
No, it's the same thing.
yes, they are. Right like this. Yeah. Are you just asking, is this notation okay? This will confuse people. So don't do this. And if you ever find yourself doing that, you're doing it wrong. Because we will never end up with anything other than dy dx, a linear dy dx right here. Because the dy dx always comes from the chain rule times the derivative of the inside. Right.
Oh, I didn't first find a line in the
Aha! It goes all the way back to our chain rule right here. I'm doing the derivative with respect to y times the derivative of y with respect to x. Good questions. Any other questions? Okay. Now, having done this, I want to identify all of my terms that have dy dx and all of my terms that do not. And I'm going to subtract all the terms without dy dx from both sides so that they come onto the right-hand side. And I'm going to clean up this term right here. So I now have these terms with dy dx on the left and these terms without. Now factoring is my friend. Out comes dy dx times all of this and we get dy dx is equal to negative 2xy minus y squared over x squared minus 2xy. And believe it or not, even though it looks like you can simplify it, there is not much simplification that can happen. Tomorrow, we'll ask, how can I use this to find interesting points? Tomorrow, I'm in my book. Yes, yes, indeed.